It's my pleasure to be the chair for this session. The first speaker is Shi-Bing Chen, and the title of his talk is The Optimal Partial Transport Problem. Please.
Yeah, okay. Yeah, thanks the organizer for the very kind invitation, and also thanks Michael for the introduction. So I will talk about the theory of the optimal partial transport problem, which is based on a joint work with Jiakun and Xujia Wang from Australia. So I think yesterday, or the day before yesterday, Jiakun has already talked about something about the classical optimal transport problem and its application. So today I will talk about a more general case, which can be seen as an extension of the classical optimal transport problem, which also arises in some applications. But my slides was made for maybe for analysis people, contains a lot of technical details. I will try to avoid them as much as possible. So first of all, let me briefly review the classical optimal transport problem. So I will. So in the classical optimal transport problem, suppose you have a source domain. For example, you have some materials, omega, like in China, with the density of materials F, and you have some factories in, for example, in USA, like omega star, with the density of the distribution of the factory with G, and then you want to transport the mass from omega to omega star in the cheapest way. So to define what's the cheapest way, you need some cost function. For example, if you transport unit mass from location X to location Y, you need to cost CXY. And then, so for a transport plan in mathematical language, we usually denote it as a mapping from omega to omega star T. And then, since you transport unit mass from X to TX, you need to cost CX, TX. And then in small portion, you do the integration Fx, dx, and then in the entire domain omega. This is the total cost for this special transport plan or the transport mapping. Then in mathematics, we want to minimize, or in real application, we want to minimize the total cost among all admissible T, which is transport plan. But if you don't impose any condition on this T, then the problem is not well posed, because it doesn't make any sense. So a very natural condition we can think is the following one. For example, in omega star, in the target domain, you have a small part of the region. This, for example, this contains some factories. This part, using mathematical language, we can think it as a Borel set. This is a Borel set, for example, Borel set A, for any Borel set A, which is contained in the target domain. And some materials used for the factories in this set is coming from this part in the source domain. So this part, you can think it's very easy to see that this part is the inverse image of A. So the materials in T inverse A, the mass of the materials here should equal to the mass of the factories here. So you need to, a very natural condition is the following one. In omega, in T inverse A, the integral of F, the total mass of the materials in this part, equals to the integral of G at A. So this should be satisfied for any Fourier set A in the target domain. And in using probability language, this one usually means the notation should be T sharp F equals to G. Basically, you can think it like you can call it T is measure preserving. Measure preserving. This is a very natural condition for this classical optimal transport problem. Also, from here, let me choose a special A. For example, A contained in omega star. Let's choose A. If A equals to omega star, then it's quite easy to see that T inverse A should be the entire domain omega. Then a natural condition appears like omega F should equals to omega star, the integral of omega of G in omega star. So in the classical optimal transport problem, a very natural condition is that the total mass of the source domain and the target domain should be equal. So here, also here in the admissible set for T is inf T. T should satisfy T sharp F equals to G. So this is this one is a classical formulation of the optimal transport problem, which is also called the Monge's problem. MP, Monge's problem. I think the problem was raised by Monge in 1781, around this time. So also one more thing is that this formulation, if you are very familiar with probability, it's okay. But if you are not very familiar, then the condition T sharp F equals to G can be written in a different way. For example, if you are lucky, T is C1, then this condition is quite easy to write it down. Just as you compute the Jacobian of T, determinant dt. This is the differential of T, and this determinant dt is a matrix depends on the location, and just equals to fx over gtx. If you move gtx to the left-hand side, you can think it's basically T is a change of variable. It's like you are at the beginning you do the integration in omega, then you do the change variable. You do the integration in omega star, but there is a mass balance condition, something like that. So this is a classical optimal transport problem. The classical formulation of Monge's problem. You see, this problem, this problem is quite difficult, even for existence. Whether the solution exists or not is a very difficult problem in mathematics. I think it takes many years to solve this the existence problem. And so I will mention later. Just like the difficulty is because in this formulation, the problem is very highly nonlinear. You see, T sharp F equals to G. This condition actually it's a nonlinear condition. If you have two mapping T1 and T2 both satisfying this condition, then the linear combination of these two mapping usually doesn't satisfy this condition. So you don't have it's a nonlinear problem. You don't have a priori estimates. Then it's quite to prove the existence of a solution. And also, this classical formulation in recent applications, for example, the image retrieval problem, usually this condition is too strong. I mean, this condition, the mass balance condition. For example, the total mass of the source domain and the total mass of the target domain should be equal. This is quite a strong condition. And also, it's in real application, it's natural to ask. So, for example, if we only transport for example, the total mass of F is, for instance, the total mass of F, for example, is 50, and the total mass of G, for example, it's like 60. But we we only need to transport total mass. We only transport mass m equals to, for example, 30. Then the question is, what's the most economical way to transport mass 30 from the source domain to target domain? For example, here is the source domain omega. Here is the target domain omega star. And heuristic thinking, you will think that like, for example, here you will pick out, you will choose 30 mass, choose a portion of domain to participate in the transportation. And for the target domain, you will also choose a portion of the domain to participate in the transportation. The total mass here in the shadow part, both are 30. And this is a very nice situation. But in analysis, we are interested in how to prove the existence of solution. What is the solution unique? Some natural question also contains, for example, there will be some hypersurface separating the mass participating the transportation and the mass not used. This part is the mass not used. And for analysis, people will be interested in the regularity of this hypersurface, which is separating the still mass and the moving mass. So these are the questions we are concerned later. But before giving the rigorous definition of this problem, I will discuss a model from the image retrieval. I'm not an expert in this area, but I just copy from some papers. I forget to write down the title of the paper. So that paper, I think the name is like the Earth movers distance and the image retrieval, something like this. In Google Scholar, looks like the citation has more than 5,000. I think you can find it on the Google. So suppose you have a collection of data. The first signature with clusters P1 to PM. You have M clusters, and then P1, P2, P3 are the representative, and the weight, corresponding weight is omega P1 to omega PM, and the second signature also with N clusters is Q, from Q1 to Qn, and then Dij, you can think Dij as the distance as the cost function, like C. This is a discrete model. So Dxy, Dij is like the cost moving unit mass from the Pi to Qj, for example. And then we want to find a flow. Fij, it's you can think it's a mass transport plane. But here, in this case, we should be this discrete case is slightly different from the case I formulated for the classical optimal transport problem. In the classical optimal transport problem, I just use the T mapping. Mapping for example, X can be only mapped to one location, but here maybe the mass can be splitted. So we want to find a flow F, capital F, and it's basically it's a transport plane. Small Fij is the flow between Pi to Qj. You can think it as a transport, the mass transported from Pi to Qj. So we want to minimize the total cost. Here, the total cost is just because it's a discrete case. It's similar to the integration, like to the integration. Then in this problem, we need to set, we need some constraints. Constraints is like this one. The first constraint is flow. Each flow is greater or equal than 0. It's a very natural condition. And then the second one and the third one basically means like the total mass transported from Pi should be less or equal than the total the weight of pi. Similarly, the mass received at Qj should be smaller or equal than the weight of Qj. This is basically it's something related to what I have said as the optimal, the partial transport. We only transport a portion of mass. But here, slightly different is they have the first condition, the first constraint. It's about the basically it means that total mass transported equals to the minimum of the total mass of the source domain and the target domain. For example, in the previous formulation, you have this is the integral f equals to 50, for example, and integral of g equals to 80. So here, like the mass transported is basically the minimum of these two quantities. It's like 50. So if f is the optimal flow, namely f is the optimal, is the minimizer of this problem, then they define the earth mover distance from P to Q is this one. They have done normalization divided by this quantity, but in analysis, this kind of normalization is not very important to study the property of the mappings. So this is a discrete model, and it's from the image retrieval. And but what I will talk in the following is about a continuous model. So I will start from here. Also, let me say something a little bit more. So for example, in the Earth mover's distance, the cost function is basically the cost function dij. Usually it's something like the location distance, the Euclidean distance from pi to qj. Sometimes, for in this classical Monge's problems, basically it means like the classical Monge distance is cxy, just equals to the Euclidean distance, so the distance from x to y. But in recent in many applications during the last decades, this cost is also quite important, equals to half x minus y squared. You can think it because it's square, something it looks like it has some kind of Hilbert structure. Also, it will be related to the so-called Monge MP equation I will mention later. So in this talk, I will also focus on this cost, distance square cost. So now let me introduce the problem. So the formulation is like this. So I will use as a measure theoretic formulation of the optimal partial transport problem. You can compare it to the Earth mover distance formulation. So here you have a source domain. You have a source domain omega with density f and the target domain with density g, and the cost function is half distance square, and it measures that transporting unit mass from x to y. The cost for transporting unit mass from x to y. So giving mass m less or less strictly, you can use less or equal, but let me assume strictly less. Suppose the mass m is strictly less than the minimum of these two total mass. This small m is the mass we want to transport from omega to omega star. Then the question is, the heuristic question is that we want to find the most economical way to transport mass from mass m from source domain omega to the target domain omega star. So, but using probability language, we need to formulate the problem in the following way. First of all, let me define a set gamma. It's the joint measure. Gamma, this is a notation, gamma less or equal than fg. It means it's a Boolean measure, which is mu is defined on Rn times Rn, and it's left marginal. This mu A times Rn, it's the projection of mu to the left, and so it satisfies the left marginal less or equals than F, the right marginal less or equals than G, and it should be satisfied for all Borel set. And this is the definition of. You can think this set is admissible transport plane in the language of measures, and you can also compare it to this condition in the Earth movers distance formulation. These two conditions, you see, this is a discrete model. So in continuous model, we can think it in, you can write it in this way. And then the optimal partial transport problem, basically we need to minimize this cost. Giving a mu, you can think a mu, this measure, basically it's a transport plane. And then for this special transport plane mu, the total cost is the integration of this one. And mu is among all admissible transport planes. And the second condition, mu Rn times Rn equals to m, it means we need to transport exactly mass m. So this is the formulation of the optimal partial transport problem. Optimal partial transport problem. And also, you see, if here in the definition of admissible set of transport planes, if less or equal or are replaced by equality, then it recovers the classical optimal transport problem. So basically, the optimal partial transport problem is an extension of the classical optimal transport problem. So we have a regular formulation of this problem using mathematical language, and so we also see that this in application, this problem appears in image retrieval around the 1990s, I think. But in mathematics, I think the first paper very rigorously treating this problem is Caffarelli and McCann 2010 annual paper. They proved that the existence of solution of this optimal partial transport problem. Yeah, they can prove. And also, what they proved is contains a lot of information, characterizations for this optimal transport plan. For example, what they proved is that there exists a subdomain of omega u, and a subset or a subdomain of omega star v, and also two convex functions u, v, convex functions. Convex function is something like this convex function. And then the optimal transport plan, you see at the beginning, we formulate the optimal plan as a measure, joint measure. And the optimal transport plan can be given by using these two functions, u and v, in this formula. Basically, it's a push forward of f restricted to the set u. So this is a very nice characterization of the optimal transport plane. Basically, it becomes a mapping. You see, basically they have found the optimal part, the best part to participate in the transportation. This part is capital V. And because basically the problem is symmetric, you can switch the nodes of omega and omega star f and g, something like this. And basically, also if you are not familiar with this push forward, what's this? I have already mentioned this push forward. It means this one. So Caffarelli and McCann have proved the existence of solutions, and they have given a very nice characterization of this solution by using mapping and the subdomains. U, V, although they are only convex functions, but the mapping basically it's the gradient of U, gradient of V. This is related to the classical Brunner's theorem. Brunner's theorem for the classical optimal transport problem. But I think Jiakun has already mentioned this. Okay, so you see, in this picture is quite nice. The mass participating in the transportation and the mass not used are exactly separated by a hypersurface. In 2D, in dimension 2, basically it's a curve. In high dimension, it's a hypersurface. Similarly, in the target domain, also the similar thing happens. And so we will call this hypersurface separating the still mass and the moving mass by free boundary. It's called the free boundary. And Caffarelli and McCann proved some regularity of this free boundary. They proved that this free boundary is C1 alpha local. In the interior of the domain, the free boundary is a C1 alpha hypersurface. So maybe I think maybe you will be curious about the things like this. Here, why is the mass are exact? For example, here the shadow part is the mass. All of the mass they are participating in the transportation. For example, if here you have 50 total mass and here's 80 total mass, you only need to transport 30. Why it will not happen that you evenly choose the mass in the entire domain? You choose 30 mass in the entire domain. Basically, it means at some point the mass part of mass is not used, the part of mass is used. Similarly, here in the target domain, you also choose the 30 mass evenly in the entire domain. Then in this picture, you see there will no free boundary. But we don't need to worry about this. We can use the following property to rule out this situation. This picture will not happen. I mean, what I mean is if at some point the mass is used, then the entire mass here, so all the mass here will be used in the transportation. Basically, it means a point either it's not moving, it's entirely not participating in the transportation or entirely participating in the transportation. So here is a interior bulb property, which is very nice. Which is this property I will explain a little bit of detail. Maybe this is the main detail I will explain today. And I think everyone can understand this property. But this property is quite important in prove some deeper regularity result of the free boundary in this problem. So let me give a proof of this. Let me give some explanation of this interior bulb property. What does this mean? I will draw some picture. So suppose you have this domain, and also let me still denote the total mass of F equals to 50, total mass of G equals to 80. We only need to transport mass 30. Then, for example, you have a free boundary. This is a heuristic explanation, but you can make the proof very rigorously if you want. So this is basically, for example, if this part mass is used here, X, the mass around the X is transported to mass around the Y here, you see? Is transported to mass along the Y. Then a very important property we can deduce in this problem is the so-called interior bulb property. It's the interior bulb property. If you know some in PD books, you will see interior bulb property just means a domain at a boundary point. You can draw a small ball inside the domain, something like that. But here, the interior bulb property is not only you can draw a ball, inside the domain, but you can control the radius of this ball. Basically, it means if the mass around the x is transported to the mass around the y, then you use y as the center and use the distance between x and y as the radius. You draw a ball. Then the interior ball property, it's very easy to understand. It means this ball, the intersection of this ball centered at y with radius, the distance between x and y. Then the intersection of this ball and the domain omega, this shadow part will, all the mass in this shadow part will participate in the transportation. Then you can see, if x is participating in the transportation, you can draw such a ball. And so every point, so all such kind of point you can draw a ball. Then, so basically it means that the active region in the source domain it's a union of such kind of set, like the intersection of ball and the domain. And but the boundary of this set, this set, you can think it as what? The boundary of this set, you can think it as the supremum of this spherical function. This one, a family of spherical function. But if we impose the conditions that the omega and the omega star, these two domains are separated by a hyperplane, this is a very important condition in Caffarelli and McCann's paper. Then not only the radius of such kind of balls are bounded from below, also the direction, the opening, the direction of this spherical function is has some uniform control. Basically, then the free boundary capital the free boundary f, basically it's the you can think it as a graph of function, which is a supremum of such kind of spherical functions. Such a kind of spherical functions, their opening is the direction of opening is has some uniform control. Also, their radius has some uniform control. Basically, it means that the curvature of this spherical function, spherical graph has some control. Then it means that the free boundary is it's very easy in analysis is it's an exercise to prove that the free boundary f is semi-convex. Basically, you can imagine like if a function, graph of function is a supremum of some Lipschitz functions with controlled Lipschitz norm, then the supremum is also Lipschitz functions. Here, like the supremum of spherical functions, it's semi-convex functions. So this is very nice. So basically, it means you see also in this picture, x maps to y. So you can draw a sphere, which will be on one side of the free boundary. Will be on one side of free boundary. Basically, say if the free boundary, because I have already proved that the free boundary is this is proved by Caffarelli and McCann. They have already proved that the free boundary is semi-convex. Semi-convex means the free boundary is like Lipschitz. Also, it means that almost everywhere it's differentiable. For example, if you are lucky at point x, the free boundary is differentiable. Basically, the unit norm is well defined, and then the unit norm is nothing but the direction connecting x and y. So we have a very nice formula. The unit normal of the free boundary at x is given by the transport direction. If two domains are separated, are disjoint, then dux and x they are not equal. Basically, that not this one is non-zero. So the unit normal, the direction is well defined, and we also see that to study the regularity of the free boundary, if you want to study the regularity of some hypersurface, basically you need to study the oscillation of the unit normal of this hypersurface, right? So you need to study the regularity of the unit normal direction of this hypersurface, but it's connected to the gradient of u. So to study the regularity of the unit normal, it's you only need to study the regularity of gradient u. But you see, from the hypersurface to its unit normal, you already take the Wang's differential, and from u to gradient u, you take Wang's differentiation. So basically, it means that to study the regularity of free boundary, you only need to study the regularity of u. But we should be careful that, for example, we want to study the regularity of u near this zero, near the origin. For example, we need to study the regularity of u at here. But the important thing is we need to study the regularity of u up to this free boundary. So this is the strategy to study the regularity of free boundary. Also, so Caffarelli and McCann, what they have studied is they need to impose some condition. One condition I have already mentioned, that these two domains should be separated by some hyperplane. Another condition is that these two domains are, both of them are strictly convex. And you can think it as these two domains are strictly convex and their closure are disjoint. This is enough. And also the densities F and G should be bounded from below and from above. Okay, so then in a very in an early paper by another early paper, you see the Figali, the publication, the time should be similar. It looks like similar, but I think Caffarelli and McCann's paper was submitted to this or accepted like in 2007 maybe. So Alessio Figali studied a more general case. He studied the situation when two domains may have overlap. For example, you have two domains, omega and omega star, but they have some part of overlapping. And then he also proved the existence and the uniqueness of solutions to this problem. Also, I forget to mention that in Caffarelli and McCann's paper, they also contain some very interesting other properties of the free boundary. Let me draw a picture here. So they not only prove the existence and the uniqueness of solutions, they also prove that some topological property of the active region. For example, they prove that this capital U is the active region. Capital U, the closure of capital U, this is path connected. They have proved this property. And they also proved that the free boundary is monotone. Monotone with respect to the mass. You see, if here is mass 50, here is mass 30. So when m equals to 30, this is the free boundary. But when, for example, when you transport mass m equal to 31, so will this happen? A natural question is that the new free boundary is like this. They proved that this will not happen. The free boundary is monotone with respect to mass. Basically, it means the free boundary goes like that, goes like this. This is new free boundary maybe looks like this. They will moving in one direction. They will not intersect with the original one. Also, I remember some other authors say studied the quantitative monotonicity of the free boundary with respect to the mass transported. So Alessio Figali, they studied the more general case, and they also proved the existence and the uniqueness of solutions, and also the free boundary in this more general case it looks like this one, and he also proved the regularity of free boundary, but needed to away from this part, away from the common region, away from the closure of the common region. So let me last one or 2 minutes. I will say I will state our main result. So major open problem in this optimal partial transport problem is this one. Suppose the domains are very nice and the densities are also nice. Are the free boundary smooth? This is an open problem from Caffarelli and McCann's paper. Do we have higher regularity of free boundary? Since in our 2000, I mean, it's like basically it's submitted. I think this year we have do a lot of we have, I mean, fully resolved in this year, and what our theorem says that the free boundary, yes, the free boundary are C2 alpha. So basically, we solve this open problem, and so in some other case, we not only solve Caffarelli and McCann's open problem, but also the method also works for the formulation in Figari's paper. Basically, we can also study the case when two domains have some overlap. Yeah, so that's the main, I think, a main story of the optimal partial transport problem and our main result. The following are many, quite a lot of technical detail, contains the technicals from real Monge-Ampere equation and something like a blow up and a priori estimator. So I will totally skip this part. It's quite technical. And also some open problem is that the regularity of free boundary when the cost is the Monge's original cost distance function. Also for general cost function, can we study the optimal partial transport? Can we study the regularity of the free boundary? Yeah, I think that's all my talk. Thanks very much.
Thank you very much for this very, very interesting talk. Thank you. Are there any questions? Well, I just want to ask briefly, so you looked at the case when this function, correlation function, I don't know what is the right term, is distance square, cost function.
Yes.
Distance square, and you mentioned as an open problem the situation when it is just distance.
Yes.
Can you explain the main kind of difference between distance and distance? What is the principal difference here?
Okay. Yeah, thanks, Michael. Yeah, it's a very nice question, right? So the situation is quite different. So let me explain a little bit about this. So for the distance square, actually, even for the classical optimal transport problem, like omega star, basically the regularity issue can be reduced to study the Monge-Ampere equation. It can be reduced to this problem. Determinant, the hashing matrix, determinant equals to fx over g dux. This is the equation in omega. And then there is a boundary condition, which is gradient u. It's a mapping omega to omega star. If the distance, the cost function is half distance square, you have this very nice equation, and you can use a PD technique like for Monge-Ampere equation. The technique developed by Caffarelli. You can study the regularity of u. The optimal mapping is nothing but T just equals to the u gradient u. This is Brunner's theorem. So you can use PD technique to study this problem. But if the cost function C equals to x minus y, you don't have this kind of equation. You don't have this. You don't have PD. It becomes a pure analysis problem. So maybe you can use something to approximate it, but seems it's not quite useful to study the regularity. I mean, for example, US, maybe a natural idea is like you use a cost function like this one to approximate this one, 1 plus epsilon. If it's 1 plus epsilon, like t 1 plus epsilon to the power 1 plus epsilon, this is strictly convex. This is a nice cost function. Maybe you will use this cost function to approximate this cost function, but unfortunately, it still doesn't work very well. I mean, you don't have equation. You can only use analysis. You don't use you. I mean, many tools are not useful in this case.
Right.
Yeah.
Thank
Even
you.
also, let me mention one more thing. In this case, there is no good regularity. There are some counterexample says that even for the full transport problem, even the densities are smooth. The mapping T maybe not smooth. There are some counterexamples.
Okay, but I mean, is it true that, I mean, from naive viewpoint, I mean, the transport cost is proportional to distance, not to distance square, kind of in a naive sense.
Yeah, original Monge proposed the question with distance, but recent years, for example, because the optimal transport problem is also connected to the fluid mechanics. In that formulation, usually we need a distance square. Right. And also, for example, like in the semi-geostrophic equation, semi-geostrophic equation in the formulation, also it's one need to use this one, distance square function. There are a lot of many, also in, for example, improving some isoperimetric inequalities in the application in pure mass, we need to use distance square because it has a very nice equation. You see, in this equation, basically it means gradient U is a very nice change of variable formula.
Right, thank you.
But you're right. Yeah.
Sorry, there is another question. Please, Kellen.
Yes. So very nice talk. So I'm wondering that it seems that I saw that many people in economics, they study that omega star equals exactly omega, but F does not equal to G, and that does sound like a fixed point theorem, and there seems to be some more result along this line. Is that correct?
Oh yeah, you are right. I'm not very familiar with what they have done in economics, but I recall that people in economics, first of all, maybe omega equals to omega star. This is okay. We also allow omega equals to omega star in the classical optimal transport problem. And maybe they are interested in cost function like this one, x to minus y to the power p, but p is greater than 0, less than 1. For analysis people, we are interested in this range, p greater than 1, because in this case it's convex, strictly convex. Looks like they are interested in this one, if I am correct.
Okay. Yeah. Thank you. Yeah.
Thank you.